So, hello everyone, and welcome to our final day of Astrosprint Discovery. And we're going to end it in a big way. We have Professor Deshpande with us, and we're looking forward to hear him. And over to Professor Deshpande. Yeah.
Thank you, Priya, and thank you, Najam. I apologize to all of them who were there yesterday. I couldn't somehow make it. So let's try to catch up on what I missed to say yesterday. So I'm going to talk about pulsar aspects. That might be a fun thing to do with, as a population study, as well as studying the pulsar time sequences. Now, here is a list of things that I'm sure you'll have it available in your other fora also. As I had sent it to Priya, she can make these things available again so that I can leisurely look at it. But these are basically places where you will find pulsar data for more intense pursuits than just playing with the extracted or derived parameters from observations. Coming to pulsar population, there are umpteen number of pulsar population studies that are possible. Of course, we would like to know as much as we can about how pulsars are born, how they are distributed, how they what they do, where they are during their lives, and how do they end their lives if they do, and what happens to them after they end their lives in cases where they have some help coming to resurrect themselves. And when they do that, how do they look like to us, and so on and so forth. So there are large number of studies that have been done over the last 6 decades, and there is still a list of unanswered questions that prompt us to revisit even the issues that are dealt with quite some time back, what presumably with a small amount of data. Now we have, fortunately, a large population of pulsars, thanks to all the big surveys that were conducted, sensitive enough to detect several thousand pulsars. Of course, these several thousand pulsars are still about a small percentage of total number of pulsars. We believe that there are about 1 lakh pulsars in our galaxy, of which, because of their beaming effect, that they radiate only in certain cones as they rotate. We are not sure that we'll see all of them, and it can even be calculated based on their cone size. And it turns out that we will be able to see roughly about 20,000 of them, of which it's nice to know that more than 10% of them have been discovered. 90% of them are for your generation to discover. But while we have information on these 200 plus pulsars, there are lots of interesting things that can be done. So the major source of data, which is compiled painstakingly by people at ATNF Australia, CSIRO, there is a pulsar catalog, and the interface allows you to extract a wide range of parameters. Some of them are directly measured, some of them are derived. Okay. Don't have to repeat this, but just to set the stage, pulsars, as we believe, are fast rotating, highly magnetized neutron stars with a well-defined rotation axis and an arbitrarily inclined magnetic axis with respect to the rotation axis. And we will have a variety of situations where the rotation axis itself might be arbitrarily inclined on the plane of the sky, as well as with respect to the plane of the sky. In the sense, it might be pointing away from us by some angle, and its projected orientation also could be arbitrarily oriented. So what we believe is radiation, among other things, comes from what are called the open field lines. This is a region where within the distance, what is called the core rotation radius or light cylinder radius, where the tangential speed is still below speed of light, and when it reaches, the core rotation stops, and whatever field lines manage to close within that distance remain closed. The others are open as seen up to that distance, but they eventually close through the medium around. But as far as the local vicinity of the pulsar is concerned, we will see them as open field lines. They let charged particles stream out along this cone, and the radiation produced by them is what we see. So, as I said, there's a closed magnetosphere, and then there is open magnetosphere, and that's the overall picture. Predominantly, we deal with dipole geometry, which has been established reasonably well from whatever clues we have about the magnetic field structure in the neutron stars, in and around the neutron stars. So I will not bore you with these details, but the typical mass is about 1.4 solar masses, radius of about 10 kilometers. So take the sun or sun-like object of that mass and squeeze it, hammer it down to 10 kilometers, what you get is a neutron star. The magnetic fields are pretty intense. Even in the case of the low magnetic fields, they range from about 10 to the 8 to 10 to the 13 Gauss on the surface of the star. Of course, then it falls off as you go out. They are rapid rotators, where the periods range from 1.5 milliseconds, which is close to the limit of their spin, because if they were to rotate faster, they would destroy themselves centrifugally, to as long as 20 seconds, and in certain cases, even longer. Okay, I'm not going to talk about how they're born and so on. I'm going to straight away zoom on to the essential aspect that I would like to bring up, but this is a background to that. So the basic Lighthouse model was proposed very soon after the discovery, almost within a year of the discovery, that we have a rotating object and there is a source of light of some sort which spins past us, and when it points towards us, we see a flash of light during its rotation, once per rotation, and that's the light we are looking at. But the exact mechanism of radio radiation, which is still not clear, but at least some clues came about through the famous polarization observations, where one saw that with the blip of light that one was seeing, if one looked and zoomed in and measured the plane of oscillation of the electric field of the electromagnetic radiation received, it followed an orientation change systematically through the pulse. And this is famously known as the S-shaped curve of the position angle of the linear polarization. Of course, this depends intricately on the variety of geometric factors, angles related to the magnetic axis with respect to the rotation axis, and how the overall system is oriented with respect to our line of sight, and so on and so forth. But the essential picture that Radhakrishnan and Cook advanced was this magnetic, what they call magnetic pole model, where the picture is that looking down the cone, the observer would see this display of the open field lines as spokes on a wheel, and as the pulsar rotates, with the observer being stationary, you can also think of the pulsar being stationary and the observer crossing across. And when it does that, you will find that the effective orientation of the field line, projected field line. This is a curved field line with this flaring, which is, bending more and more as you come out away from the star. But in projection, it will look like a straight line. If you look at the plane containing the field line itself in projection. So you will find that this orientation, which will be, if it's tagged to the radiation that we receive, you will find that this orientation on the plane of the sky will make this angle, and then later this angle, and so on and so forth. And this angle will keep changing. And this is precisely the detailed shape that has been seen. So this works beautifully. And of course, as you can imagine, that if I were to cross close to this, I will see more rapid changes in the angle for the same amount of movement of the observer's locus. And this thus gives us a handle on how close we are to the center of the pole, center of the, or axis of the magnetic field of the pulsar. And based on the orientation of the overall system of this magnetic axis with respect to the rotation axis, we will have the standard geometric effect of, it will take a small amount of time to cross certain angle versus take less time to cross larger angle if the inclination happens to be very small. It's like, you can walk through the entire longitude range if you're close to the pole of the Earth, right? By walking small distance. Whereas on the equator, you'll have to walk long distances to cross the same amount of longitude, right? So this polarization position angle sweep changed the way one can derive information about detailed geometry of the pulsar. It was found to be independent of the observing frequency, and so it gave a variety of clues about the nature of the radiating particles, that they are high energy particles with high Lorentz factors, which combined with the fact that we see so much intensity from the pulsars had forced us to invoke coherent radiation. That means large number of charged particles have to radiate together in phase for us to be able to see the kind of intensities we see. That combined with the fact that we have high magnetic field, that it doesn't allow the particles to stray out from the path that they took initially, adhering to a given field line. They will be stuck on that field line and they will move like beads on a string throughout their journey outward from the pulsar surface to the outer region. And this together told us that the radiation will come in narrow cones along their local tangent as they move along the field line, and they will be radiating in big bunches containing large number of particles radiating in phase, so that their intensities are proportional to the square of the number of radiating particles, rather than a simple sum of incoherent contributions, which would have been proportional to only the number of particles instead of square of the number of particles. So the emerging picture is very simple, that we have beams of radio radiation emanating from large bunches of charged particles flowing outward at relativistic speeds, and it can explain both the intensity of the radiation, which is very bright because it's coming from a very small region to produce so much intensity. You will have to imagine as if this is not the physical picture as if there was a black body at temperature of 10 to the 30 degrees Kelvin to match the equivalent radiation we receive, which is of course some form of synchrotron radiation. In the presence of magnetic field, these charged particles are radiating, they're gyrating, but the gyration radius being practically zero, because as soon as they try to deviate from the field line, they're punished. And the fine is the radiation that they have to give out in terms of the transverse momentum that they had. And so the transverse momentum is radiated instantly. Only the longitudinal momentum is surviving, and that picture keeps changing as they move along the curved field line. And so strictly they adhere to the field line that they began on, thanks to the high magnetic field. Okay. Now pulsars also radiate the radio radiation at the very frequency at which they are rotating. This is the magnetic dipole radiation, and that is intrinsically at very, very low frequency, but that's the major energy loss from the pulsar. For a long time, one believed that that's the only energy loss, and people used to use that to compute even the strength of the magnetic field at the surface using the formulation that we can measure the rate of loss of energy that we can infer from looking at the way pulsar slows down, and then equate that to the radiation from magnetic dipole. And then that gives you, matching these two will give you some estimate of the magnetic fields. And all the numbers that we've been mentioning so far about the magnetic fields have come from that. But this radiation doesn't get very far because of the medium immediately even surrounding the pulsar is filled with plasma. Even the most thin plasma, like in the interstellar medium, has a plasma frequency of a few kilohertz, and we are talking of this few hertz radiation trying to go through this medium, which is, of course, the passage is blocked. And so this radiation pushes the medium and some equilibrium size is achieved, and it leads to formation of a cavity around pulsars. So pulsar nicely sits inside the home that it makes. And of course, what I described just before coming to the slide was the radiation we see in radio, which reaches us and which is very intense at frequencies below 1 gigahertz. And this radiation has a steep non-thermal spectrum, which is characteristics of pulsars, unlike other non-thermal sources. It's much steeper. So essentially what it means is at lower frequency, you get more intense radiation. Okay, so this is the formula that I was talking about. We have general evolution of isolated pulsars, where the pulsar rotation slows down with time because we are radiating energy in form of magnetic dipole radiation predominantly. There is also loss of energy due to particles which are flowing out, which are carrying a significant amount of energy, as it turns out, which we'll see an example of. And this loss of this comes from the reservoir it has of the rotational kinetic energy, and so it costs in terms of the rate of spin, and because of which the dynamo weakens, which produces this intense the primary charged particles, which lead to generation of this large number of particles we require necessarily for producing the coherent radio radiation, and that causes death of pulsar if the dynamo becomes too weak, and so on and so forth. Pulsars also go through glitches, which you must have heard of. I'm sure Sushan must have, or some of her students might have talked about it. I will not go into the details of it. But what happens to these pulsars after the dynamo becomes too weak is they cross this line, which means at a given field, the dynamo, if it becomes too weak, after the period has lengthened, so they move along horizontal lines typically. And when they hit this red line, which is inclined in this diagram, there's a different combination of a certain combination of the magnetic field and period, which decides the dynamo action. And so this is sort of certain strength of the dynamo. Okay, fixed strength of dynamo will have a line like this, dependence on the magnetic field and the period. So when it crosses it, you land up in what is called the graveyard. And there is no hope of this pulsar ever getting back on its feet unless it meets or has a companion which is willing to resurrect it by donating some angular momentum, the orbital angular momentum associated with this binary motion, and deposits some matter, which people call accretion routinely. So the accreted matter brings in angular momentum, and then they can be brought back depending on where they have landed during the time before they receive the help. The help is available on different time scales based on the companion mass. If it's a very massive star, it's ready to give help pretty soon. Whereas if it's an intermediate star, it might take tens or hundreds of million years before the help can be provided. That means the accretion can begin. And then they can be brought back here. And the classic case of low mass X-ray binaries, where the lower the mass of the star, it takes a long time for it to evolve to the level where it can help the companion compact star. And that is the birth of so-called millisecond pulsars. So they can be spun up to very short periods. And those are found in low mass X-ray binaries, which you must have heard from Monomita. Okay, it turns out that most pulsars are born in binaries, and depending on the companion, of course, survival of the binary, their life history gets sketched. Okay, so this I already mentioned that we have about 1 lakh pulsars in our galaxy, of which we expect to see roughly about a fifth of them, which is about 20,000. We have already 10% of them, and the rest of them are waiting to be discovered by you. So their distribution in our galaxy is something that you can look at, and that has got lots of clues about the progenitors that they have. One such example was talked about by some of the interested folks working with me for since the last session. Okay. Now these are a variety of pulse profiles seen in different pulsars. What is good about it is that the signature shape is characteristic of a given pulsar, and this is stable over days, months, and decades. So far, we have seen that they don't change. Sometimes they might have two signatures, one for the personal life and one for the official life. And they switch between the two without any warning. But largely, most of the pulsars have a single signature, and this also accompanied by the characteristic position angle swing phase curve that we saw, one example of. And these together define the real identifier for given pulsar. Of course, as I said, this S-shaped signature, the exact shape of it depends on the various angles that are involved in the way we sample the magnetic field orientation. Okay, if you look at individual pulses from connect some device to look at the time sequence of intensity changes, this is what you will see. Now you will see that these are pretty erratic and noisy, but after once you use big telescopes and and combine data over a wide range of frequencies and so on. You can get individual pulses that are much more clearly defined, as in the example on the right. But even there, you will find that what you see in one rotation differs vastly from what you see in the subsequent rotations. One might wonder, where is this famous signature that I just talked about for individual pulsars? None of these pulses look like that. But it is only after integrating, averaging these over thousands of pulses, that thousands of individual pulses, that we achieve the average pulse profile, which is the signature that I talked about. So you will find there are issues involving the way radiation comes about at different regions, at different frequencies. It turns out, by studying the way the profile evolves as a function of frequency, as you go from higher frequency to low frequency, you will find the shape undergoes some modification. And the most important modification is suppose there are two components, the separation between the components increases monotonically as we go to lower and lower frequencies. This has led to the understanding that there is so-called radius to frequency mapping, in the sense that the highest frequency radiation comes from closer to the star, and lower frequency radiation comes from much outer region. And as you can see, that the dipole field line, the last field line which define the cone size in angle, keeps on increasing in the angular width as we go outward. And that's simply a manifestation of the dipolar geometry of the magnetic field. So it confirms both the pictures, that we have these charged particles forced to be on the field lines once they start on a given one. And so that's what defines the way the radiation comes. And the radiation depends on the curvature of the field line, which is also consistent with the fact that we expect lower frequency radiation coming from the outer regions. So this has provided some clues. So this way, one has collected information across a wide range of frequencies about large number of pulsars. This I already talked about the need for having large number of particles radiating together, but without coherence in emission, the way we have, none of the radio pulsars would have been visible at the distances which we see them. So what it requires essentially is a large charge or current density, and how to generate that. And that is done by this mechanism where we have a huge amount of, let's see. All right. So what we have is the dynamo working, much the way it works on the what we used to use on a bicycle, where we would have a magnet being rotated, and the EMF produced by that, we give it to a small bulb, and as we pedal faster, the light will glow brighter and all that. So what we have here is analogous situation where a huge magnet is being rotated fast enough that it generates electric field and a potential difference which is of the order of 10 to the 12 volts. Now this 10 to the 12 volts potential difference causes rearrangement of charges everywhere else except in very small region around the pole where it survives. Elsewhere, the electric field gets cancelled by the rearrangement of the charges in response to the electric field. And only in this region where the rearrangement is not possible, that we have about 50 to 100 meter high region just above the surface, which is called the polar cap region, where we have 10 to the 12 volts potential difference. Now you can imagine that if you throw in a charge there, it's going to get accelerated to ultra high energies, relativistic energies, and here tera electron volt kind of energies. And those charged particles interacting with the magnetic field will produce electron-positron pairs. Now, within this region, if an electron-positron pair is produced, you don't require any guessing to know that one kind of charge will move one way, the other kind of charge will move the other way. And that's what happens. The charges move downward, and they also can produce pairs. The other sign of charges moves outward, and they also can produce pairs on the way. So what first, the detailed mechanism is the following, that you have charged particles accelerated to very high energies. They emit gamma ray photons as they move along the field lines locally. The gamma ray photons interacting with the magnetic field produce electron-positron pairs. The electron-positron pairs are again like the accelerated charged particles, and they do their turn of emitting gamma rays, and the gamma rays in turn produce pairs. So this cascade can go on, and you can have an avalanche of charge pair production. But all this depends on the seed pairs, right? Whether they are energetic enough and how energetic they need to be. They need to be able to produce at least one pair. And you can see that the 2 times mass of the electron times c square will be the typical energy, minimum energy required. So when the acceleration is not able to produce even those energies, there is no hope of producing cascade of charged particles, let alone even a single pair. And then there is no hope of any coherent radiation, and that's when the pulsar dies as a radio pulsar. So the exact mechanism of how this coherent amplification happens is entirely unclear. Many people invoke mechanisms like some kind of a laser or equivalent here, maser mechanisms. Some people invoke plasma processes which have nonlinear behavior and amplification. Essentially, you have regions of negative optical depth, which amounts to amplification and so on. So there are a variety of ways of viewing it. In practice, I'm sure the pulsar magnetosphere has arrangements to do the right thing to produce the radiation that we see. We are trying to figure out that from a distance. So there is no consensus on that yet. But what is clear is there is enormous amount of coherent amplification that has to occur. Okay. One has tried to get rich clues about these things by using a variety of behavioral patterns that one has seen in the pulsars, including drifting subpulses, nulling, that something that Sushant might have talked about, profile mode changes, which I just talked about, when some particular pulsar might have 2 signatures, stable signatures. It might go from one mode to the other and return to it without warning. We have a lot of information about the geometry and everything else from polarization observations, and polarization position angles also show sometimes orthogonal jumps. A particular S-curve is largely followed, but once in a while it deviates and follows an S-curve, which is exactly shifted by 90 degrees from the original one. When we zoom in on short time scales, we see details going up to microsecond structures, which tells us that the real emission is spiky emission. And it's really the occurrences of those microstructures in bundles that tells us about the detailed components and so on and so forth. You also have sometimes giant pulses, which are sometimes 1,000 to 10,000 or 100,000 times the normal intensity of the pulsar. People have tried to understand that as well, and there is large amount of work done. But these are additional clues. And as it happens in many cases, with more clues, they also bring additional challenges of understanding certain details. instead of clarifying the original thing for which we had sought these clues. Some of the mysteries or uncertainties or gaps in our understanding have been filled. And one classic example I cannot resist mentioning is a part-time pulsar discovered by Kramer et al. In 2006. This pulsar comes on for a few weeks and is on a holiday for the rest of the times for several weeks, and then comes back again and so on. What was seen, we said we know that the pulsars slow down and the period keeps on increasing, or the frequency of rotation keeps on decreasing. So that's the way it would have slowed down over the period it was observed. But during the times when it was active, it was seen to be slowing down at a faster rate. That means it's like a person spending money at certain rate and becoming poorer and poorer. But if it does that on the average at certain rate, when it was actively going and shopping, it was spending more quickly the money. And this led to our understanding that this is in addition to what is seen as the loss due to the magnetic dipole radiation, which is always present regardless of whether the pulsar is active in radio or not, because that's the local spending that it does. It's like the general electricity bill and the rent that you need to pay, and this is the extra shopping. So when it spends more, and it does that when it's active, it has told us about the other important energy loss mechanism, and that is through the particle flow and the large flow of charged particles carrying energy away from the star. And that also slows down the pulsar, and it slows down distinctly differently, so much so that if you make an estimate, it turns out that the amount of energy lost through the particle flow is comparable to that due to the magnetic dipole radiation. What is nice is when one works this backwards and finds out from these observations what would be the current density and the charge density and so on and so forth, it is found to be consistent with what Goldreich and Julian estimated right in the beginning, soon after the pulsar discovery, within a decimal place. And that's the triumph of the theory that I would like to always fondly underline. All right, I will not go into the details of this. This is about the giant pulses and the nanosecond structure. Sometimes you can also see diffraction patterns associated with coherent radiation coming from a certain spatial extent. So there are multiple clues. I will also not go through the drifting behavior, except to say I wanted to keep this figure because I just wanted to highlight that we have this cone of radiation seen from the top or looking down on this cone, and the magnetic field will appear to be coming towards us, and there will be some electric field component which might be perpendicular to it, sort of tangential to the local surface, and that these combination of these two will make the charged particles feel E cross B drift, which will cause them to rotate about the magnetic axis. And when this happens, given our sight line, we will see some given region might go past us, our line of sight, and that leads to their apparent location within this pulse window that we see appear at different locations. And they do that very systematically, as you can imagine, because the rotation, if it's a stable rotation, then each one of them will come, make their presence felt, they will change their location as they go along, and then move out of the view. And this is seen, and these are famously known as the drifting subpulses, which have given a variety of clues. You can if this rotation is stable, you can put them back to create a picture that you otherwise cannot see. For example, out here, when we sample this cone through this sight line, we are sampling a very thin slice. Okay, the thinness of the slice is the Lorentz factor of the charge particle. I think there is some echo. Okay. All right. So that's how thin region we are sampling at any given time. Of course, the extent of the core is sampled. So we really do not know what is there in the rest of the cone, but that can be found out if one were to see systematic drifting in such a way that we are staying put at this fixed location and the pattern is rotating past us. Instead, we can think of it as the pattern is being fixed. We can sit in this in the rotating frame and ask how the observer sampled the cone. And you will find that we have sampled it along these chords for successive pulses. And when this information can be put together, you can make an image like this if we happen to be sampling this more centrally. That means there are no gaps. Okay. Otherwise, there will be a hollow region that we can never sample, which is interior to this picture. And the size that we will miss is this size marked by the beta, okay, which is the closest we can get to the magnetic axis. All right. So when that distance is small, you can actually get, these are like they're having the diametric cuts. And then as you rotate the pattern, you have cuts along different diametric sections, and then you can put them together to form this. So what is seen here is that there is patchy emission. There are discrete emission sites, and we see radiation from them. It's not fully lit. This is important for some aspect that I'm going to mention now. So of course, these patterns appear to be quite consistent across frequency. So it lends support to the fact that we believe that what is happening along one field line at some lower distance is followed up and evolves into what happens at larger height and so on and so forth. So if you see 20 sparks, as in this case, you see exactly 20 sparks in some other frequency, which is sampling the upper heights. And the rotation rates inferred from them are identical. So one can actually construct a picture by conducting observations at multiple frequencies, and you will find you can make tomographic measurements of this cone sitting here. Okay. So now, how much time I have? Let me check. I'm not watching.
Yeah, lots of time.
So I will probably halt here and ask if there are any questions on the material that I've talked about so far.
There was something on the chat, but my thing logged out and logged in. So
I'll just check now.
one second, I'll just tell you because
No, nothing. There is one question.
Does the mode changing happen due to switching on and off
correct,
emission
correct.
components in the cone? No, it doesn't. It's not that one of the components is switched off. The entire shape itself changes. So there is, sort of not something where only one component or few discrete components have been switched off. The overall shape and the smoothness of it remaining changes to another smooth signature. Of course, then you can identify, you can say that, oh this looks very similar to the other mode signature, and maybe we can think of this as one intensity increasing of this component and so on and so forth. But it's not always possible to do in all pairs of switching that we have seen. So Prathamesh, does that answer your question?
Yes, sir.
Okay, Sanket has a question. What is the strength of radiation radiated from charged particles on the closed magnetic field lines? Is it detectable? Firstly, they are not highly relativistic particles in that, right? If at all there are some particles trapped, they might be doing some communication from one pole to the other. The radiation, if they were to give, we would have seen radiation from them in the so-called off-pulse region, and people have been looking for it, not found any yet, or there have been claims which are not substantiated and fully confirmed yet. So one believes that even if they were to be radiating, they certainly have no mechanism to create bunches and radiate together. And that alone, that fact alone might make their relative contribution almost negligible. As I said, even the present pulsars that we see, if somebody is to go, where to go there and just tell all the radiating particles, don't radiate coherently. Keep radiating the way you are, but don't radiate together. We will not see the pulsars. So what might be missing there is large energies and the coherence. Okay, Prathamesh has another question. Does nulls relate to switching off of these? Yeah, null relates to switching off of everything. It's like the power shutdown. Okay. The generator itself somehow is quenched. The initial primary energetic seed particles, accelerated particles themselves are not generated. It appears so. Okay. So people are trying to see whether it's like a capacitor, and the capacitor is sort of shorted for a while for some reason. Then you won't have the potential difference available for charged particles to get accelerated to the kind of energies we need them to do the eventual part of the recipe of producing radio radiation. So it appears like the entire machinery is switched off, so much so that all components vanish. It becomes inactive in radio, and was very nicely highlighted by this part-time pulsar, which has the lull periods are actually the nulls, long nulls, weeks long. Does that address your question, Prathamesh?
Actually, participants can unmute themselves also if they wish, or put on their videos also. Yes, sir. He says yes. Okay.
All right.
I think you can proceed.
Okay, if I can proceed. Now I'm going to basically bring up an issue that has not, that has nagged everyone, and it's a bit of embarrassment. So while I have mentioned this as a potential pursuit that you can take up, or one can take up with available archival data, it's by no means something where success is guaranteed. Okay, but when you walk that path, you will be enriched on the way, that is assured. So let me bring up the kind of radiation signatures that we see from these pulsars as a function of frequency. Now, this is how it looks, where frequency is plotted as on the x-axis and the intensity or the pulse energy plotted along the y-axis, or average flux density, whichever way you want to represent it. So you will find that it increases towards the low frequency. Sometimes there might be turnovers where it reaches the peak intensity at certain frequency, and if you go further down, the intensity, instead of increasing, decreases. Reason for this turnover is also not understood. Sometimes it flattens. Largely, it has single slope in the log-log representation, which means you can say that the flux density is proportional to frequency to the power some constant. And the constant here will be negative, given the fact that the radiation intensity increases towards lower frequencies. So these are typical spectra constructed from a large number of measurements done by various people and so on. There are also instances sometimes where you get, after dropping the intensity to very low value at very high frequencies, beyond several gigahertz, at much higher frequency, you begin to see more intensity. And this had prompted several people to actually go and make observations at tens of gigahertz. And actually they found that indeed some pulsars shine back more brightly at much higher frequency after this low intensity regime at certain in-between frequencies. All right, but I'll not go into the details of it, but what I want to stress here is measurements are available only at certain discrete frequencies to us. By combining them from different frequencies, we try to get this picture. And of course, when we talk of amount of radiation, we should be talking of the entire integral of this, right? But traditionally, only measurements are available at 400 megahertz largely, because that's where most of the pulsar observations were done, and 1400 megahertz. So 1400 here. So these two being the favorite frequencies, large amount of data are available. And that's not true for all the pulsars at other frequencies, although they have been as many attempts and so on. So if you look at the spectral index, as I showed here, the spectra don't seem to have a fixed slope. The slope itself changes and so on and so forth. But even if you take the central region, let's say, of the prominent part, let's say 100 megahertz to 1 gigahertz range, and calculate what the spectral slope is, you can see that it has a distribution. As I said, the numbers have to be negative, because nu to the power some negative number will ensure that you have increasing intensity towards lower frequencies. So even there is large distribution. But you can see that most of the non-thermal sources in the sky have spectral indices in this range, okay? Sort of more like 0.6, 0.7, and so on. Most of the galactic and extragalactic background, which is non-thermal, has that kind of spectral index. Whereas pulsars are, one of the hallmarks, spectral hallmarks of pulsars is their steep spectrum sources. That means they are more easily visible at lower frequencies. And one of the classic examples of that was this first millisecond pulsar that was found, which was a source seen by Bill Erickson in his low frequency maps, which did not have a counterpart at high frequency. And that implied the fact that it was not even visible in the high frequency map meant that the rate of change of intensity with frequency was very high, which meant high spectral index. And that's when they suspected that this must be a pulsar and not some arbitrary object, and they made a systematic search for it and found that during observation, targeted observation done from a receiver. And that was the discovery of the first millisecond pulsar. So the flux density itself is used even if it's available at one wavelength or one frequency. The intensity is multiplied by the distance square, and that is called a quantity proportional to the luminosity of the pulsar. And you will find that the luminosity of the pulsar itself is very different. They don't have they are not like standard candles. We will see the difficulty in looking at the radiation. As I initially said, the major energy loss mechanism is the dipole radiation, magnetic dipole radiation, and then almost equal amount of energy is lost or similar rate by the particle flow. But what we see in radio is a tiny fraction of it, okay? Less than even 1%. So now, like Rad used to say, that we are standing outside this big machinery, a big factory, and we do not know what is going on inside. And we are trying to figure that out from the small squeaks of this that we get from the machinery while it's operational. And we're trying to make out, based on that, what is going on inside. So the energetics of stuff happening inside is hardly related to the intensity of the sound or squeaks that we hear. And that's exactly similar situation in the radio radiation that we receive. The amount of radio radiation we receive hardly relates to what is happening inside and the energy losses or the general energetics per se. So you will find that if you were to ask for how the luminosity is distributed, many people have modeled that, and you will find that it's sort of has a mean intensity and certain spread, which is very wide in comparison. Okay, and if you plot the cumulative distribution of that, it goes like the way is shown here. So that's what we know about the radioluminosity. People have tried to plot them in different, this is very early work. I just want to highlight this early work just to show that people began to worry about it right in the beginning. So this is the luminosity distribution of what we saw was the cumulative distribution from Manjari Bakshi. Here, Manchester's diagram shows directly the probability density distribution or the number distribution across the different luminosity bits. And you will find that it ranges over several orders of magnitude. So there is nothing appears to be unique about it, other than the fact that this is a bell-like distribution, no further clues. Of course, these are other things in the figure, which I will not comment on. Okay. If you take efficiencies, these are calculated by several people as recently as 2014. If you take luminosity in a particular band, be it radio or be it X-ray or some other band, and divide that by the total luminosity. Total luminosity is nothing but the associated with the energy loss rate. And that can be measured directly. How do we measure it? We measure the slowing down rate. We know the spin rate. And if half I being the moment of inertia times omega square was the energy, kinetic rotational energy of the star, we can measure the rate of change in it, which would be given by I omega dot. Omega can be measured, omega dot can be measured, some assumption about the moment of inertia can be made, and then you have the what is called the mechanical luminosity of the star. So this is what is used at the bottom. And when you look at that, you will find that there is seemingly some correlation between the radio efficiency. This is efficiency, not the luminosity per se. But even that is spread over the energy, right? So you will find that more and more loss rate exists. It relates lesser and lesser to the radioluminosity, right? Which is pathetic. So, so this is something that doesn't help much, but we need to take this into account. Whereas in the other wavelengths, it doesn't even have that trend, right? It doesn't seem to depend much on the energy loss rate at all. The efficiency seems to be, here, the efficiency in other wavelengths seem to be completely not following any particular pattern. Okay. So this is the question: can we seek some handle on the radioluminosity from knowing the mechanical luminosity? And this work has been visited by a large number of people, something that I would encourage you to do. As I said, there may not be any guarantee of success in it, but one has to be at it and see by accounting for several aspects, we can get closer to it. Now we saw one of the aspects which is never taken into account so far is the fact that I gave you an example of this drifting subpulses, and I had drawn a small locus of the observer across the cone. Now, if the cone is completely lit and you are sampling only a tiny fraction of it, right? And that's what you call your radio pulse energy, what you saw during that. You will find that it's neither corrected for the geometric effects nor corrected for the fact that you are sampling only a tiny region of this, what otherwise might be a very bright cone. And depending on each one of the pulsar and its geometry, you might be sampling different regions. But you naively take that intensity and call that as a radial luminosity of the pulsar, and then begin to compare that with the mechanical luminosity of the pulsar. And so it's not surprising that you do not get a good dependence on the mechanical luminosity. So one needs to begin to account for several effects, okay, which affect the way radioluminosity calculated from naive measurement of the pulse energy and putting the distance estimate, which itself might be wrong or uncertain, but assume for the time being that that is as good as it can get, because now we have better estimators of the distance given the better description of the electron density distribution in our galaxy. So knowing the dispersion measure, one can get a reasonable distance. It could still be wrong by 10-20%, but that is not going to make a large error in your luminosity estimate, because here we are talking of luminosity estimates which do not relate to the mechanical luminosity and differ by orders and orders of magnitude. Whereas half an order of magnitude uncertainty due to distance is not going to hurt. So investigation is required to see how things are affecting the way we measure the radio intensity, and from that we are going to the town by saying this is the radioluminosity. We need to take into account wherever possible information is available, how we are cutting the cone, what is the magnetic inclination, how does it affect the overall energy loss, including that from the particle flow and nulling, and so on, and what this overall radiation coming from the entirety of the cone and not just the cut that we take, relates to the loss of energy rate, the rate of energy loss and the pulsars, which is the mechanical luminosity. So this is something that I would like to pitch as a domain where you can do something original and challenging, because there are a large number of projects doing more of the same. But this is one aspect that I've chosen, something that requires a careful accounting for several effects and bringing this subject on some grounds which are robust. I will stop here before I go on to the next one. There might be questions related to this.
There don't seem to be any questions as of now. Come on. These two were done. Okay. Yeah, please, questions. You can unmute yourself also if you want.
I think somebody is trying to ask a question. Probably the voice is too low.
Yeah. I don't know. One second. I'll just check. No, that is probably me mumbling.
Oh, I see.
Yes, we are.
Anil, there is some background sound. Oops. Yeah, I think you can go on, Desh.
Okay. So just to that even when you look at these efficiencies, remember that the spreads are of the order of, even for the efficiency, okay, the spreads are of the order of few orders of magnitude, okay. And so there is really almost randomness here because of the normalization, okay. You see this negative slope. This is a trap that you should never fall in, because it appears from this diagram that there's a beautiful correlation. What you have done is taken some number, divided that by some number, and plotting it against that number. Regardless of whether this has got any relation with this at all, you will see this inverse correlation, because you're plotting a quantity on the y-axis and inverse of that on the x-axis. You will always see a 1 upon x kind of pattern. In log, it will look like a straight line. So please don't be fooled by the apparent relatedness here. What is really reflected well is here, that the mechanical luminosity seems to have nothing to do with the radioluminosity. Okay, so this is the true picture that you should be looking at. And what one is asking is, are there things here which each one of these points, having been plotted here blindly without accounting for several specific reasons why the point is here and why not the point here or up above this. And that has got to do with the several aspects that I mentioned. And when that is done carefully for all these pulsars, I won't be surprised if a particular trend emerges. Okay, so that's the hope. Several people have studied this, plotted this, and tried to mindlessly fit some curves to it without asking why this scatter. Are there some essential reasons, obvious reasons that one should correct for? And I have just listed a few that one should already take into account while doing this. Things to do with the piece, small part of the information that we have instead of what is happening across the entire cone. We also have information limited to only one or two frequencies, whether we are taking integral of it across the entire frequency range. The lower frequency may not matter much because the energy contribution from that may not be as significant as the higher frequency might be. So after everything has been corrected, if there were to be any nice relation between the two, it would begin to emerge. It's always easy to spoil the relation that might exist, or the signatures of the signatures of the relation, by not being careful about accounting for various effects that might be already affecting the measurements. So that's the main point. Okay. All right. The second part I'm going to suggest is modeling of pulsar wind nebulae. And I'm going to show you one example that we have done, particularly in modeling the radio counterparts of it, which have hardly been studied except in one or two cases. Now, this will involve even finding out the images of in X-rays of regions around known pulsars, and they might have a faint or noticeable nebulosity around it, and the nebulosity might appear like some weird blob of X radiation, but if you look carefully, you might begin to see something which is relatable to a region specifically produced and what should I say, painted by the pulsar. Okay, and I'm going to show you one example of it. So this is the story of the Vela pulsar. This is a beautiful X-ray image of the nebula, which was made by Helfand and collaborators, including our friend Richard Dodson. In order to study effect of or seeing corresponding signature that might appear in X-rays, they were mainly interested in X-ray intensity. If the X-ray intensity underwent any change when the pulsar glitched. In the process, thanks to the Chandra capabilities, it produced a beautiful image, which led Helfand et al. To even theorize and explain the morphology that one saw. All right. This is the radio image associated with it. This nebula is a tiny, tiny fraction in size of this entire region that is covered by the radio nebula, which is not surprising because lower and lower energy particles, as they are able to go away from the location where they started, can continue to produce the radiation. And in fact, the radio radiation is dominated by the relatively lower energy photons. And the higher energy photons are produced here. And so they will require energetic particles. And as particles lose their energy on the way, they will produce lower and lower frequency radiation. And so if you go to, this is a picture at 1.4 gigahertz or 8 gigahertz, 4 bands. So this is, I think, for one of the bands. If you go to much lower frequency, you might see even a bigger region associated with this nebula. Now, modeling of this kind of a region is not so hard, as I will try to show. So people understood this X radiation as due to the on these arcs and what they call the jet, as resulting from equatorial wind, which dissipates its energy in form of synchrotron radiation, and the arcs are basically highlighting the shocked regions, bright regions, and in between it should have been a patchy region like this, and the in-between region goes to low radiation, low intensity radiation, because the magnetic field changes its sign, and while changing the sign it goes through a zero. So that's the explanation given by Helfand et al. Okay, remember the size of this object that we're talking about is several light months. Okay, then we tried to see what natural explanation exists for this kind of morphology, and we have proposed that these are traces of radiation beams where the particle flow is coming out. Remember, we invoked large number of particles, relativistic particles, to produce the kind of radio radiation, coherent radio radiation that we see. But then we completely forgot about them. We never asked what these particles do other than carrying energy from the pulsar that we saw in the part-time pulsar beautifully. But what happens to these particles? They're streaming out at relativistic speeds and carrying huge amount of energy. And so if you seek that answer to this simple question as to what happened to these charged particles, you will find that they encounter this wall that we described, central cavity, created by the pulsar itself. And then they hit the wall because the wall has high density and lose energy. And the loss of energy there produces this beautiful glow at the location of the place where the particles hit. Where will the particle hit? The particles will hit where the cone intercepts the wall. And the cone is not everywhere. The cone is confined to a certain solid angle associated with the open field lines. So that's our picture. And if you really look at this object and look at the traces of the bright arcs that one saw, what we have is each one of these poles with charged particles is like a paint hose. And then we're going to paint the wall of the cavity and it will draw a circle. This circle viewed at some arbitrary angle will appear like an ellipse. If the region closer to you and where the radiation is pointed towards you is going to look distinctly brighter than radiation produced by particles moving away from you, that's pretty natural. And so you will see brighter regions in this regions. Now, when this region is bright, the other hose end is pointing away. But during one rotation, it's going to come around, right? And light this part and so on and so forth. So, but yeah, and this is the part that you're going to see bright. So now if you relate this picture to the picture that we had, you will find these were the arcs and they fit perfectly to this picture, okay, for the inclination angle that we know for this pulsar and the overall orientation of the system. So these are traces of pencil beam of particles flowing along the magnetic axis. Then you can ask what this jet is. People believe, the prevailing belief is that there are particles moving along the rotation axis, much like the, the quasars that you see, right? Or microquasars. But here, this is not an accreting object. This is an isolated object. There is no reason for any action along the rotation axis. Okay. In fact, it's difficult to sustain any flow, let alone energetic flow along the rotation axis here as for an isolated star. So it's not only unlikely, it's unphysical to think of such a flow. So what is this radiation that we see? So this is not a particle flow, but what we see, what we believe is that as the particles flow outward along this pencil beam, you will find that well away from the pulsar, where the core rotation has stopped, you will have magnetic field wound up. It's no longer the dipolar magnetic field. It will be a toroidal magnetic field. So it will be spiraling out. And now it will be like a cage with wires running in planes perpendicular to this axis, right? Now you shoot a charged particle and ask what will happen to the charged particle. The charged particle will feel a force, a Lorentz force, which will make it deviate from its direct path because it was trying to move perpendicular to the magnetic field. The magnetic field will exert a force. Combined, the magnitude of that force will depend on the velocity of the object, the velocity of the particle, as well as the strength of the magnetic field. But it will be in the direction which will be along the, if the particle is trying to move this way and the magnetic field is that way, the force will move it up or down, depending on the sign of the charge and the field. So you will find that there will be spread of charged particles across to a wider angle in only one direction. It will not spread in that direction. So given this, it's like taking a thin brush and painting the wall, and now taking a broad brush and painting the wall. What is the result of it? The broad brush will paint this, and much like the pulsar through the pencil beam we see as a dot flashing every period, we will see the broad brush length flashing every rotation, and that's the jet, so-called jet. There is no physical particle motion along the rotation axis. So this is simply a flash in the pan, as you would say. So you can explain the diffuse radiation and the jet through the broad brush painting on the wall. We have already seen what the pencil beam, the narrow beam or the narrow brush will draw. It will draw these two arcs and a dot corresponding to the pulsar. And when combined, you will see this. It's a beautiful match for very simple, modest assumptions. You will find that this appearance is going to be different. Oof. Let's see. Can I get these things running? I think I have. Let's see. Okay, so this is another example of the crab pulsar. Let me just go through that and then run these movies to show you how things will appear. So this is just the crab pulsar, and there is twist of the jet and so on, which is tied up with the precision and all that. Okay, something that you can figure out even by looking at the image. So this is how it appears. If you model it with minimum assumptions, this is how it will appear for a spread of energies and so on and so forth. With that apart, what I want to highlight is, firstly, these writings on the wall can be seen even in cases where there is no pulsar detected. Remember, we see the Vela pulsar and we have looked around that because of some other reason, and we found this beautiful image. There could be images in X-rays of the nebulae without the pulsar being known, which is right in the center of it, or the specific location of it. So you can see, you can keep your eyes open for such nebulae that you might see, and there might be a pulsar there. There might be associated arcs and jets and nebulosity associated, which one can relate to if one knew what to look for. And I'm going to show you some examples of, other than the modeling of it. Okay, so I think this is where I put them. Let's see. Okay, the variety depends on spelling mistake. All right, so let me quit from there, and that's what I want to show you. I want to show you these examples. I think they're here with me. Screen sharing is stopped because the share screen is closed. Okay, so let me share the screen again. Where am I? Okay. So I'm going to change, I'm going to share the screen again because it, okay. Is the picture visible to you, which is changing?
Yes, yes, it is.
Okay.
Yes.
All right. So this is a simulation of what this nebula would appear in successive frames if the viewer was located differently or the nebula was oriented differently with respect to us. Okay. So this is for a specific geometry. Okay. Of the pulsar. What is changing is the observer's orientation. Okay, again, I think the same. Maybe I should share the entire screen maybe. Maybe that will make it easy. Share screen.
If there are multiple windows, better to do the whole screen.
Huh?
If there are multiple windows, then it's better to do the whole screen.
Yeah. So optimize share. Where is the possibility of, okay, this screen. Okay, now can you see it? See my entire?
Yeah, we can see your entire desktop. Yeah.
Okay. All right. All right, so this is the view of how the nebula would appear, okay, with different orientations. What we saw is just one manifestation of it, okay, but you can see the huge variety. This is assuming a certain parameters like the Vela pulsar, okay, but if you had narrow cones, okay, the spread was not large. This is how it will appear. So there are two things I wanted to suggest. One is, if you were to be looking at X-ray images or radio images, you can look for nebulosities. You may not see such arcs and so on in the radio images, but you will see certainly the diffuse regions, much the way I show one example of radio. You will see certain symmetric structures, okay? Sorry, switch that off. Okay, all right. So these are two examples, and you can also do it with the wide angle thing, how it will appear and so on. So it's easy to model these things and view them in images that you have the sky at reasonable resolution. And who knows, you might even find pulsars, which are much the way, just to drive home this point, let me display this other picture of the Vela and tell you something. Okay, the picture that you see here, you have seen two arcs, and we argued that the two arcs are relating to the two poles, radiation from two poles. It turns out that for the Vela pulsar, although the two poles are the radiation from the two poles is visible at high energies, X-rays and gamma rays and so on. The interpulse, which is resulting from the second pole, which would have been a pulse between the main pulses, halfway down 180 degrees apart in phase, is not seen in radio. But we can see the unseen pole contribution, okay, here readily. And you will find that by looking at these images, not only you will see the unseen pole among the two poles that you should see, of which you might be seeing one pole, but even you might see radiation from both the poles when none of them is visible. So they could be pulsars which are never going to beam towards us in radio, but they have made a painting on the wall of the sky, which you can look at and detect their presence. So let me stop at this and see if there are any questions. Okay. Looks like there are no questions. I mean, people must be tired after the 11 days. I'm just trying to see if there are any familiar names in the audience. So this is a completely new lot of students, right, who are attending this time.
Yeah, quite a few are new. Yeah, most of them are, many of them. Yeah.
Desh, what we thought was the ones who did projects with you earlier,
Yes.
we can make them mentors this time.
Yeah.
So if any of them they are interested, so at least the initial part they will handle it, and then when required they need you and more serious work. Then because
This is regarding what? This is regarding this
regarding-
project, the projects that I mentioned.
yes. So at least
Yeah,
today,
but that depends on, you should check with them probably.
yes. So we'll be listing all the projects which will be offering.
Later then, yeah, I'll be sharing a Google form where people will then put in their intents and then we'll get back to you.
So there are a few old ones. Today, you see there are 2 or 3 who had been there even earlier.
Right.
But I think none of them who worked with you, I think. Yeah, just one. But many are new ones. There are a lot of new entries.
I see.
So this is going to give them a glimpse of everything. Shushan Kunnar did something.
Right.
Then, yeah, Tim Hamilton, and then we'll share the projects, and then we'll see how to proceed, because we can't be getting you into wasting or spending a lot of time all over again. So those who have already learned from you, they can initially at least spend time with them, and then yeah. So we'll share this Google form, and then we'll get back to you.
Yeah, you take it in any direction. I was just tossing these ideas for anybody to take. In fact, you can also probably put up a form for people who might want to volunteer to mentor. Okay.
Yes.
Yeah,
Yes.
that's a good
Exactly.
idea. That's a good idea.
Okay.
So,
Because there might be large number of people if this is the subject, right? There might be other people who have been thinking about it or haven't thought about it but are interested, and they are already the more familiar lot, right? Who
yes.
would be playing mentor role more naturally because of both
Yes.
their sheer interest as well as
Mhm.
instead of uh, just assuming that the people who are working with me presently might be in a position and willing to do what you were just mentioning. Okay.
Yes.
Yeah, that's right.
No, they can initially start off with, I mean, those who are interested and who feel they are.
Yeah, depends on what the commonality of it is, how much
Yes.
they feel confident
Yes.
take on such a responsibility, because it's a big responsibility, all said and done, right?
Yes. And they can always go back to you or
Yeah,
anyone
Then it
whenever
becomes
they have.
difficult. But then it becomes a brokered relation, which is not good.
yeah.
Yeah.
All right, so I'm just telling you the shortcomings of such a possibility,
Okay.
Yeah.
but I think the better way could be, more proactive way would be to say that these are the projects, these are the students interested. Other people who are already experienced in the field might be interested in this in these projects, and they are welcome to take the mentorship role.
Mhm.
Yes.
Okay.
That may, you might get even people who are not right now associated with the forum might come forward, because now the
Mhm.
scene is
Yeah.
sort of the platform has been created, a topic has been defined in which they can ask themselves whether they are interested, and then then there's nothing, no better situation to ask for.
Mhm.
That's right. So we have tried all these three modes. The first set was we started in August till December.
Mhm.
I remember every Saturday, Sunday we had 2 2 hour sessions,
Yes.
and during the week people were interacting over Telegram or WhatsApp,
Yes.
and then they broke up into groups and did projects. The next set was when we started with Enterprise, which was 3 days of
March.
lectures,
Right.
where we had from morning to evening lectures for 3 days, and then they continued. This time we thought that 3 days of continuous lectures on Zoom is a bit heavy, so we
No,
tried.
this was a good pattern. Yeah. Mhm.
Yeah, so this went on for 11 days.
Mhm.
Yeah. But
Um,
I'm going to take the feedback from participants to know whether it really was or
yeah,
not.
the first
Yeah.
one was the best, but it went on for a long time, and that was a time when
And
everybody
that's
was
and why it
locked up.
went on so well, because that's when everybody was stuck at home. So people were
And
logging on. We
Yeah.
had many
yes,
more people,
But
80,
now
90.
they have other pressures, other
Yeah,
pressures of
that's right. That's
classes.
and they have other pressures. We also have other pressures. Our universities have
Right. Right.
started. Then we were teaching agreed, but only online. But now
Mhm.
we have to go
now we are
regularly.
going to work.
Yes.
Right.
So and then most important is the participants. They have started with their universities, institutes, and exams and various other
Right.
things.
Right.
Yeah, that's right.
Okay, so thanks a lot.
Oh, not
Do
at
we have
all.
questions? Do we have questions? Uh, I think these were covered. Okay, yeah, these were covered. Do we have any questions? So actually, to the participants, what I'll be doing is I need to update that projects page. I have not updated it. I'll update it and then circulate a Google form so they can register for the projects they want. Until then, people can finish watching the videos which they've missed, because I'm sure there are lots of people who could not consistently watch on all the 11 days. So they can go through all the lectures. By then, we list it. And then I'll get back to you all as to who's logging in for what. Yeah. And then obviously you can decide as you wish whether you mentor or the seniors mentor or everybody together, whatever. Any model will do. Right. Okay.
All
So
right. So Thank you.
Thanks a lot. Thank you so much.
While you might want to continue the discussion for the next steps in your enterprise,
Yeah.
I can take leave if there are no further questions.
Yeah. Thanks a lot. Thank you. Yeah.
Okay. All the very best.
Thanks a lot.
You and others.
Yeah. Yeah. So do we have any comments from any of the participants? Like what sir was talking about was, is this model better working on 11 days or was it better marathoning on 3 days? Anybody has to say something? Devi Smita, Mudasir, Avantika, what would you all say? Which model was better? 3 days or this one?
In this one, ma'am,
You
it
like-
is very light and we can adjust 2 hours per day. And
good, that's nice.
yes, ma'am.
So actually, I'm going to send mail today, tomorrow to participants to, complete watching all the videos, the ones if they've missed or if they want to rewatch them. And then I'll be sharing a Google form where you can actually select the projects you want. And depending upon what's there, we can have groups and people can work on their projects, right? And the tentative plan is that there will be a third workshop, which is next generation. And next generation would be either most probably in hybrid mode. We will have an offline element, definitely. Or we can do it hybrid because I think a good number of you all are from Bangladesh, right? Some amount of you all are, not all are from India, right? So, and we don't have funds for international travel. We can give some amount of domestic travel, but not international. So we'll probably do it in a hybrid mode so that people can attend offline and online. And this should be hopefully sometime in November, December, depending obviously on the COVID condition. So if COVID disappears, then we'll hopefully have it in November, December. Okay. And if the COVID situation is still bad, then we'll be extending this thing such that we'll have that offline workshop, the hybrid workshop, which is going to be called next generation. We'll have next generation next year, depending on how, the COVID situation changes, right? So I'll be keeping in touch with you. Like I said, till then, go through the lectures which you haven't gone through. I will send out Google Forms for registrations where all the, where might be the physical meeting. Okay, so 2 Sri Lankans here. Okay, this format is better. Okay, I was not seeing your comments. I'll just see that. So, great. So 2 Sri Lankans here. So the physical meeting might be in Hyderabad itself because that's where we live. It should be Hyderabad, easier for us to organize. And so it should be Hyderabad. And but like I said, when would it be depends upon the COVID situation, right? Because it should be, people should be able to this thing. But then that one will obviously not be 11 days. We'll have to do it with 3-4 days, right? Our lectures with lab work should be well arranged on the website so that we can use them again. Exactly. So that would be my next job to work on after this thing gets over. To this thing, the website, you'll have all seen that page, right? This is the page. 1 minute. So I'll show you all the page. 1 second, I'll just get that one. No, 1 second. So I'll you actually go to the AstroSprint page, right? And you all can, I hope, see my screen. So on the AstroSprint page, on the right hand side, you'll see a part which says projects. Okay, so you click on projects and come on to this. These were the ones which I had listed after the enterprise workshop. Okay, so there was N-body sims, gadget sims, X-ray data analysis, AGN spectra, pulsars, etc. For some of them, the links are there. For example, for gadget simulations, this is the gadget download link if you want to download gadget. And where did that page go? Okay, where did that page go? I don't know. I have too many tabs. 1 second. Yeah. So the links are there. For example, the gadget commands are linked over here, and the X-ray data analysis also have connected over here. But what I basically need to do is to add these other projects. I will add these other projects on this page, right? and they'll all be listed over here. These are the earlier ones. I have not put these ones. And what you all will have to do is register your project here, in the sense you take this link. This link will get you onto a Google form, and you can now here put in the project you will like. These are the older ones. These will still be ongoing. We are not stopping these projects, but we'll be adding on some new ones based on the sessions that we've had in this time. So I'll add these things, and based on that, we will have the list of people who are working in a particular project, and those I will also put up and send to you all, so that people working on the common project will interact with each other, as well as get in touch with the mentor for that particular project. Okay, so just give me some time to do that. I will soon send you all the whole list with all these things, right? I need some time to make that, but I will do that and send that. Ridyan asked me, how many hours will we need to contribute per week for the project? So that is, see, all of you all are, it's up to you. It depends on what you are doing the project for. If Tisha asks, can you do 2 projects? Yes, you can do 2 projects. There is no such binding. It's a democratic world we live in, right? So even how much time you put into a project also depends upon you, because it depends upon how far you plan to go with it. Like the project which we yesterday showed you, which Mahmood was working on, the machine learning one, day before yesterday. No, yesterday. I don't know. Day before. So that finally, like I said, it went into a publication, and we're already doing another one, which is also we'll soon be submitting as a publication. Even the students who work with Sushan, as well as Professor Deshpande also, they may culminate into publications. Some of the students who did it, I have one who has not attended now, but he actually used it for his MSc project thesis. So that was his MSc project thesis. So it all depends upon what do you want the project for? Are you looking for PhD admissions, or is it for publications and stuff like that? Or is it just for a part-time thing? So it's up to you how much you want to do. It's up to you whether you want to do 2 projects or 1 project. You have to decide that according to you. The more you do, the less deep you will be able to get into a particular project. But so it's up to you. We are going to be democratic about that. You choose whatever you want. But obviously, if you go finer, you'll go deeper, right? If you narrow down, you go deeper. If you go broad, you will go broad, but you'll go shallower, right? So if you go in for many things, it will be shallow. If you typically go in for one particular thing, you will be able to go deep. So it depends upon you and what's your purpose and what you are comfortable with, right? So the forum platform is available on the website again. We can again show that to you. So if you actually go on to our website, right? You all need to make a login, right? So if you have a login, you can get onto the forum, and once you're onto the forum, in the forum, actually it has not been activated, we need to do it. Here what we are going to do is I will make the forum, I will make each group specifically for a particular project, okay? So for example, I will state that this one is for the Pulsar project or whichever projects. I will list the people who are there in a particular project in these things, and you all can accordingly work together, okay? And the forum will be transparent to everybody, so that everybody, whoever's interested, can have a look at this, right? So I'll put this at the forum also, it will be there. But in short, you can put in all your things over here. And I hope that will be a nice way for all of us to interact, right? At present, a lot of, unrequired stuff is there. This has not been put by me. Sorry, it's just some this thing. But I'll clean it up and make it better, right? So we'll stop with this. We'll stop with this and say bye-bye to you all. But the bye-bye is not for a long time, because we do hope that you all register for the projects and you start working on them. And thanks, Iftisha. So like we said, the purpose of this is to get you into professional astronomy. How do you actually start doing some projects? How do you start actually doing the work? So that's our basic purpose. And so we wish you all the best, and do keep in touch. You all heard the student presentations of the previous projects in this time. So obviously people who do projects now can present in the next meeting, right? So we will have student presentations. I also want to give a short advertisement. The advertisement is that we are soon having another thing, which I want to show you. This is, there are robotic telescopes. In the last meeting, we actually spoke about it. But there is something called the Las Cumbres Observatory, which has a whole set of, robotic telescopes. And these robotic telescopes, they are basically placed all over the world. So you can see this on the global map. You can see it covers the whole, northern hemisphere, southern hemisphere. We are also, we run what is called Shrishti Astronomy. So we are Global Sky partners with this Las Cumbres Observatory, LCO. And therefore, what we are doing on the 2nd and 3rd October, this would be a 2-day online workshops on observations with the Las Cumbres Observatory. So what we are going to be focusing on is star clusters and plotting their HR diagrams. So on the first day, on the 2nd of October, we'll talk to you about photometry, about magnitude scales, about extinction corrections, and we will end the day with actually, putting observation proposals and observing live with those robotic telescopes. Okay. And then on the second day, that is the 3rd of October, on the 3rd of October, we will actually show you how do you view the data which you get from LCO. This would be the form of FITS files. So we'll show you how to view it with the SAO image of the DS9, as well as we will show you the aperture photometry toolkit, which is an APT. This is a very user-friendly toolkit, which works even well on Windows. And we will use that to do the photometry, that is to measure the brightness of the stars of that star cluster. And then that very data will be input into TopCat, which will be used to plot what are called HR diagrams for star clusters. So on the first day, on second, we'll talk even about HR diagrams. So we'll cover photometry, HR diagrams, extinction, magnitude scales, all those things, the theory part on the second. And we will start observing. And on the third, we will actually handle the data which we have, do the photometry, do the plotting with TopCat, and we'll end up with HR diagrams for star clusters. And we'll actually show you how to get the distances to star clusters and their age, etc. The registration link is over here, and all our videos are always on YouTube, as well as if you register, we will put you on Zoom, and the Zoom link will also be provided with which you can actually do it. And obviously, these are not, we don't charge for any of our workshops. We don't charge anything in case people are concerned. So do register. The idea of this is that this is kind of to couple our astronomy from archival data, because in that people were already using ready data. Here we are going to actually show you the process of how do we actually get data from telescopes, right? So that's what we are going to see and study, how to do that. And that will be done on our workshop. So I would urge you all to register for this workshop. So the registration is, okay, how do you register for the workshop? I will just now give you the links, and just a minute. So if you're on the Telegram page, I'll put it on the Telegram page. Otherwise, I'm putting this over here. Please cut, paste it, and keep it for yourself, right? And you'll see that this is the website we've made for it. Okay, Shashi Kumar asked how much time for a project to present. It all depends. For publication, it all depends at the level at which you're doing what kind of this thing. So at present, I can't tell you how long it can take for publication. There are people who claim they even publish papers in a day, in the sense they do work in a day and that's sufficient for them to publish their paper. So it depends. There are people who work years on a single paper. So sorry, Shashi, I don't have the answer to your question. But so do register for our workshop. After this, we'll be having a hackathon also, but I will declare that a little later. Once we start moving this, we are going to have a hackathon in October. This is also October. So yeah, October itself, we'll have the hackathon also once we are done with this, right? So do keep in touch, and I'll put it on your Telegram group. Yes, that's true. Yeah, I'll put it in the link in our Telegram group. Yeah, I'll put it on the Telegram group. That's right. So it's, I'm already putting it over there. And okay. Okay, fine. So see you all. Have a nice time. and we'll keep in touch. Yeah, bye-bye. Naja, bye.
Yeah, bye bye. See you.
Yeah, see you. Bye-bye.